Hello and welcome. Here we are in lecture 7 talking about decoupling. So I'm going to cover what decoupling is and motivate that in just a minute. But before that, it's kind of worth appreciating where we are, right? So we've been learning more and more about Chisel and Scala. And so in our last lecture, we talked about encapsulation, right? How to kind of package the things we've been doing, both using some of Scala's utilities in terms of, how to use Scala objects or Scala classes to kind of contain things, how to use recursive functions. We also talked a little bit about using option types in order to have optional IOs. And so we're going to take that all a little bit farther today. In particular, we're going to talk about case classes, which is another Scala feature for how to kind of encapsulate things. I included in this lecture and the last lecture because I'm just trying to spread out the amount of Scala class features there are. And so far you'll learn about Scala classes, Scala objects, and Scala case class after today. That's like three. I think there's like four more. So we're not going to cover all of them in this class. Scala's got a lot of class stuff in its hierarchy, but we're kind of spreading it out. But the real thing is about the coupling. So, okay, so what's the coupling? Well, the coupling is helpful for two big reasons. One, it's actually a good way to design hardware, right? When you're designing hardware, at some point, you're going to have certain things interacting. And the coupling means there's some amount of, ability for one object to tell the other side, you know what, I'm not ready for data right now, or I do want data right now. And there's some kind of, two-way negotiation about how one data is going to be transferred. Without the coupling, things are tightly coupled. That meaning, that one is producing data or another one's consuming data, and they need to be exactly in agreement and tight lockstep about when the data transfer is going to happen, right? So you can imagine if one side maybe wants to change its internal architecture to perhaps process data at a slower or faster rate, the other side also needs to change too, right? So these two things are kind of tightly linked. And so by decoupling, by having some amount of flexibility between the two things, not only makes it easier to design and get correct, but also makes them more reusable, right? If we're trying to build these generators, well, these kind of building blocks you can plug and play in different hardware designs. If they have very strict timing rules, it's a lot of work for anybody interfacing with them, right? If they're decoupled and they're a little more, flexible, then it's easier to kind of integrate them. So it helps both for design in general as well as for reusability. Okay, so first we're going to do case classes, and I want to point out, as I promised, we are running off of binders. So this thing does work. It does take a little bit longer than I would like to launch notebooks. I don't know why, but we're running in the cloud, so this is kind of fun. Uh, and hopefully it's all going to work. So we're going to let it download all the Chisel packages. Might take a little bit longer because I don't think it has a cache, but that's okay. We can wait a minute. Um, so you can see, it's, of course, there's actually quite a few bit more packages than you realize when you start getting dependencies to pull it all in to support what we're doing. And boom, we got them all. And now we need to bring in the imports. And we're rolling. Okay, so let's talk about case classes first. So case classes are a Scala feature, and it's kind of an unusual thing where we just learned about classes, and now I'm telling you there's an other kind of classes. So what is other kind of classes for? Well, case classes can have some variety of convenience features. So they're like a class, like a special type of class that has some things that are really nice and kind of easy and built in. That's why we like them. Now you may say, well, that's great. If these are good features, why aren't they part of classes all the time? The reason why is some of these features perhaps are things you don't want all the time, or in order to make some of these features, you need to be willing to accept certain restrictions or constraints. And so that's part of why Scala has so many different types of class-like constructs, is because depending on the usage scenario, you may want or need certain things. And so a case class is more restrictive than a regular class, but because it's more restrictive, it's kind of like a specialized class. You can kind of do more things with it, right? And so what are some things it has? Number one, it already has a companion object, right? So in this case, you have a case class called movie. And so, yeah, you can just say, hey, movie, you only say new movie. Okay, that's a small thing. Um, what is more interesting, and this is what makes case classes so useful, is all of its parameters are automatically public. I don't need to mark them as vals. So that's kind of the best way to use case classes. It's kind of just like a way to have a handy way to bundle data together. So perhaps in a lot of programs, you might have situations where you have, a couple of variables you want to put together, maybe, usually like a tuple, two or three variables together. And you got to remember when you're programming, okay, wait, the second one is this, the first one is this, the third one is this. With a case class, you quickly associate types and names of them. So that way someone else can kind of read and understand what's going on. Um, And what's also nice about it is, even though this isn't technically an object, right? You get lots of for free, right? So you get things like converting to string, comparisons, copy. We'll see these in just a second, right? So for example, here we have a case class called movie. For now, we actually don't even need all this. I can even comment this out, right? So hey, it's just called movie. And yeah, we can instantiate one like, calling like this, give it a name, a year, and a genre. And we can, read a field. We can make another one. So maybe I'll just do the first one. Just run this real quick. Okay, sure. So we made a case class called movie. We made instance, no problem. Didn't need to say new. And you can see here's the default, printing of it, right? I didn't do anything to make this print. So if you just want to kind of quickly develop something to kind of hold together two data values, is really helpful. Now, some example of the things it does nicely. Let's say, okay, if I want to declare another one, okay, another movie, The Avengers. Now, this one's from 1998. It's a very common movie name. There's multiple movies called The Avengers. So let's say I want to make another one that represents the newer movie. Sure, right? And so what's cool with this one is you can just say dot copy. This is a method built in automatically to case classes, and you can override an individual field. So you say, I want just the same as that prior case class, but I want to change one thing. I want the same title, same genre, I'm just changing the year. And so, yeah, for so far, we've kind of had these, example generators. We should take, a couple parameters in at the top. As I start getting more sophisticated generators, taking in more parameters, we're going to start using case classes to kind of package that thing up, because a case class is a much more kind of way to encapsulate things. You can do things like easily, checking very certain values. It's all public. Case classes are immutable by default. You can mark things as var to change them, but I wouldn't do that. I would instead make a new copy with the dot copy. Um, but also, I mean, it's not just a data holder, right? You can put a method on it, right? So here in the original thing, we define a method that did some stuff on this, work, right? And then we can go ahead and, label what decade that movie came from, the 1990s. Cool. Questions about case classes? Yes. Oh, the question about a case class is the copy method deep or shallow copy? Um, I'm gonna guess shallow. The reason why I'm unsure as a veteran Scala programmer is because if things are immutable, you don't typically uh, come into this issue, right? So that's one of the things between deep or shallow. If you never change anything, it doesn't matter. If you do change things, you're right, it does matter. I would suspect it's shallow. Great question. Um, Another thing you can see kind of here, uh, this is going to come back to this in a month from now. We're going to see that when you have some of your data structure with these case classes, we do something called pattern matching, which is really, really cool. It's like something I've never seen in many other languages, but that will be relevant far down the road. Cool. Yeah, this is kind of one of these weird things. The Scala has this case class that's really, really handy, and then we'll see later on it's even more elegant with this pattern matching. Okay, so as promised, we're going to use this to kind of as a way to package up parameters. And so for some of these lecture slides, sometimes we really kind of try to just make these artificial examples that are small to fit on the slide, but you guys still see we're going with this, right? So let's say, for example, we're doing our counter from before. So this is mostly the same as we had before. Just now, rather than taking individual variables, we're taking in a case class, right? In this case, it has only two variables. You can imagine maybe in a problem more deserving of a case class tree, we might have like maybe like 5 or 6 variables, whatever it is. But okay, we have two parameters. They go into the case class. We can even derive some stuff based on them, sure. And then now within this counter, class, we can read those fields out, right? Okay, yeah, we can go into CP and get the width. Okay, that's what we use for declaring our width of various things. We can go pull out the limit. Okay. We can pull out the starting point. And in the case of our case class, you also give it default values, right? So our initial one is going to count up to 14. Uh-oh. Did the Scala import not work? I'm going to give it one more try and say shucks, and we're going to launch our own local Jupyter. We tried. We really tried. Um, we did try, folks. Okay. So yeah, I don't know why it didn't load correctly, but we are going to great. And is this one gonna run? Okay, we're in business. All right, so yeah, we're gonna run locally. We tried Binder. We tried. We tried. Um, and okay, so we can see the case class. There's already Verilog down here. It's cut off, but we kind of know it's going to be in there, right? Um, what's interesting, for example, on reset, it goes to 0, right? If I wanted to have, let's say, starting at 2, yeah, fine, you can start at 2, right? And so that's not too crazy. Um, so yeah, so this is kind of that scenario, right? So we can kind of have a case class is kind of a tidy way to pass around parameters. And we can read the fields out of it. We can have derived values with these kind of internal methods. Cool. Yes. Yeah. Okay. So let me repeat this for recording. The question is, okay, why are we using? So is the value of the case class the with method, or can we use a bundle or something? Um, great question. Yes. So you're right. I could declare, something like, counter IO as a bundle, and in there I could, declare these fields and also a width field, etc. The case class is more for parameters, right? So bundles are normally for aggregate types of chisel things, aggregate types of, would it be ports for an IO or, UN essence for whatever you're doing. A case class is more an aggregate type for Scala things. So in this case, we have Scala parameters, and so that's where I would want to use a case class. Now, in the case of a bundle, you can have Scala fields in there that aren't chisel types. So you can kind of use it for both. So in some ways, it's a little more versatile. But a bundle is a regular Scala class, so it can't do some of these things that case class give you. Things like, the automatic, two string if you want to just print it for debugging, and that kind of stuff. Otherwise, actually, it's a great point. So if I go back a slide, or actually even here, right? What if I say, um, will it let me do this? It might not. We'll see. If I just try to instantiate this, oops, number of parentheses is not right. It's not a builder context. Okay, shucks. But if I had a class that didn't require chisel, when you try to print it, you're just going to get like an address, right? You get, okay, my counter instance at, some number, right? And so if I want to see the fields internally, it's kind of like, okay, I got to start writing more print statements to kind of dive in there. Case class already has a toString, right? You also can do comparisons, right? So it does comparisons by the contents rather than the exact memory copy. So if you want to just say, hey, do I have these two case classes, are they the same? Sure. Or if you want to compare certain fields, yeah. Yes, question. You mean using this field? Mm-hmm. Oh, great question. Great question is so, hey, here I defined something called width, and is this a function or a variable, right? Great question. So, um, uh, this gets into a deeper issue about Scala, about the difference between def versus val. Um, so in terms of when they're evaluated, in terms of, when it's declared versus when you call it. So, yeah, so def is going to be kind of like a delayed execution in some ways. Um, but the short answer is this is a method, uh, but it looks like a variable, right? Because yeah, it doesn't have any parentheses. There's no arguments to it. We called it without calling any arguments. Remember in Scala, even if we did have arguments here, we wouldn't need the parentheses down here because if you have a no argument function, you can call it without parentheses. And it's encouraged to call without parentheses if it's immutable. If there's no changes to anything, it should look like a field. In the case of this particular operation, I could declare this as a val, and it should probably also still work. Yeah, but you could have a function there too. It could be a def. So like the prior slide, we had a def there. It actually was a function that was called. But this function, even though we say actually same thing, right? We could also you know, transform this into val. We can leave the type declaration on there. Um, yeah, that also works, right? So uh, some of the language folks behind Scala actually consider this a feature, right? The idea that, that is this a field or is this a function that's immutable? Should you really care or no, right? Um, in the case of this, you can imagine a case class, since by default all the parameters to case class are immutable, anything that's kind of derived from them is not going to change values, right? Um, the question is just when is that immutable value derived? Is it derived when you declare the case class versus is it derived when you access it or evaluate that with a def? That's the question. But I mean, these are very subtle language points that, once again, if everything's immutable, not going to matter. Good questions. Yeah. Um, cool. Okay, so the case class was kind of an opening warm-up point for today, to kind of show another example of encapsulation, and we'll be using case classes quite a bit in this course to, at a minimum, encapsulate parameters, but later on we'll actually encapsulate more. Um, cool. Okay, let's go back to our original scheduled plan of let's talking about decoupling, right? So in this case, we're going to think about the scenario where you have two components, right? You have one producing some sort of numerical value or data, another consuming that data, and right now we're thinking of a scenario of, okay, the producer is sending data to the consumer, right? And the challenge to this is how do both sides know when they're actually transferring data, right? Is the producer actually sending data or not sending data? Is the consumer actually able to receive data, right? You can imagine maybe in the simplest case, the producer sends one element every cycle, the consumer processes one element every cycle. What could be simpler than that, right? What would be harder with that? That's not too bad. But you can imagine you start building more sophisticated things. Maybe rather than just being a simple, one word wide thing, this is actually, like a larger computation, maybe a whole network frame or something, network packet. Then there's some more ability to kind of have not always sending or not always receiving. And so you need some sort of way to kind of mediate this. So the question is, how do you control this? Now, this small little case of hardware, which you may have already seen before, is actually an instance of much more common patterns throughout computer science. And the question is, how do you distribute control? So control is somehow multiple entities and they're interacting. How do you do the control for this? And well, in particular, you have a centralized or decentralized, i.e. distributed control scheme. And it turns out the reason why we're talking about this is there's a trade-off, right? There's scenarios where one is better than the other. It's not always automatic, which is the best. And so you can think about this in the very different scales, right? So you're talking about this in terms of hardware, but think about this in terms of computer systems, right? You can think about, okay, do I have a, cloud service? Okay, that's probably going to be decentralized, distributed. Why is it centralized and distributed, right? Versus something else. And so thinking about this more abstractly, kind of what's going on is that there's kind of this trade-off, right? So typically, speaking very broadly in this sense, if something has centralized control, that means when you're controlling it, you're playing it all out. You kind of are aware of everything that's going on. You have all the information available to you, you have all the levers available to take action on it. So in some ways, it's simpler to implement, right? You have all the information. You don't need to second guess on what someone else is doing. You just tell them what to do, right? So that seems like that'd be easier, right? Why do we not do centralized control? Well, the issue is there's sometimes when it's impractical to build centralized control, right? Maybe something's too far away, too high of a latency. That's why, for example, on cloud services, they have, distributed control. Or other times, you need to be distributed or decentralized because you have two components that aren't being made by the same person, right? So if they're being at different times, they're from different sources, they're not going to have the same control. And so it's kind of this question of, okay, well, shoot, well, then when do I do one or the other? Well, um, depends, right? If you have something that's really, really small, being made by one party, you probably want to do centralized control. That's going to be really easy to get right. That's going to make your life a lot simpler. However, once you get beyond a certain scale, you're kind of forced into distributed, decentralized. Additionally, if you have multiple producers, multiple people making components, you have to kind of go decentralized. So it's kind of this common trade-off, right? And so it's kind of an interesting thing. So maybe give you a more concrete example of this. You may have heard something called Rocket Chip, which is a RISC-V system-on-chip generator. So originally it was made by Berkeley grad students. Okay, they had, a core in there, they had some caches, great. And you wanted to put more stuff in there. Sure, you want to put more things in there, more parameters, sure. Then all of a sudden they graduate, found a company called Sci-Fi, and now they want to start putting IP inside the rocket ship. And the issue is, as they make more and more IP components, if they didn't change their strategy, every time they add an IP component, they would need to change the central portion of the rocket ship to be aware of the existence of these other components, right? Like, okay, I need to, have parameters for IP block A, parameters for IP block B, parameters for IP block C. And especially when they're keeping rocket ship open source versus they want to have proprietary IP, this was not the situation they want to be in, right? This is not. And so the answer is that they go from centralized to distributed, right? Where instead of having, the internals of rocket ship from the beginning know every possible component and every possible thing, you couldn't know it all, right? There's hundreds of now components that go for rocket ship. And so instead, they have something called diplomacy, which is actually a really cool Scala technology they built on top of stuff where you can add IP components to rocket ship. And then in a phase as part of chisel elaboration, these components talk to each other and they kind of become aware of each other and they negotiate various things. Like, okay, if I'm plugged into you, I'm plugged into this network. Okay, well, you can take address 0, I'll take address 1, you can take address 2. So it does a lot of sense. It's actually this handshaking protocol that's going on at the elaboration time to negotiate all this. But it's more of an example of what I'm bringing this whole long story is. It's an example of distributed control, right? It's an example of doing this. And at first, it may sound really complicated, like, oh my gosh, this is so hard, right? To have this thing called diplomacy. If you want to make a module, you need to pick this diplomacy protocol in order to actually be included in a rocket ship. That seems hard, right? But as hard as that sounds, understand the alternative is even harder. The alternative of having somehow maintaining rocket ship to be aware of, hundreds of IP blocks and constantly doing that, it's not scalable, right? It's not going to work. And so by able to speak this protocol, you can kind of make it more distributed, more essential. And so same things here, right? You can have this common trade-off between centralized versus distributed. When things are small, you want to go centralized. When things are big, you have to go distributed. And at some point, you got to cross over. And so uh, today is much simpler, smaller scale. But even still, this issue of having distributed controls can come up, right? Idea we want to have is, hey, producer consumer are different components from different generators, perhaps. We want to have a little bit of decoupling between them. And so to have that decoupling, we need to be able to indicate the inability to receive data as well as I'm not sending data, right? So if I'm not sending data, I want to be like, hey, I'm not sending anything, so don't process this garbage on the wire. And alternatively, on the receiver end, you almost say, hey, I'm not ready. Or some people might even call this back pressure, saying, hey, stop sending me data. Okay, maybe I'll pause for questions on that very abstract stuff before I get to the concrete. Okay, so let's get to a more concrete example. So there's something called ready valid signaling, which is this is a general thing that is far beyond Chisel or Agile. This is classic thing in Verilog, VHDL, et cetera. And so the convention is that we're considering a one-way link. Even though it's a one-way link, you may notice there's wires going in both directions, right? Because the consumer needs to be able to apply back pressure. So you have the payload is sent on these bits. This could be a multi-bit bus, right? It could not just be one wire. It could be 1,000 wires, whatever. And of course, with Chisel, this could be a bundle, and it could be a lot of fields inside of there. You have these one-bit wires, right? Valid and ready. So valid is the producer saying, hey, right now I have data to send. It's available on bits. Ready is a one-bit wire from the consumer saying, I'm ready to receive data. Like I actually am able to process this. Suppose I'm not busy. So in other words, if this is 0, that's the consumer saying, I'm not ready. I'm busy. Don't send me data, right? Likewise, if the producer has valid set to 0, it's them saying, hey, I don't have any data to send, so don't worry about it. So when does data occur? Transfer occurs when both ready and valid are true at the same time. So both the producer has something to send and the consumer is ready to receive. If both of those are true at the same time, on that clock cycle, we're going to consider this payload to have gone over to consumer. So let's say we do that on one cycle, and then the next cycle, we have the exact same pattern on all the wires. That means the producer is sending the exact same data over again as a second piece of data, as a second data frame, the second data transfer. Cool. Questions on this so far? Okay, so this is a general scheme. So this is something that's way beyond Chisel or Agile. This is a common kind of hardware design technique. And we're going to see how to do this in kind of in Chisel. So in particular, this is such a common technique. Chisel, use stuff in a standard library to make this easy, right? And although in this class, occasionally I will show things manually for sake of making small examples that fit in lecture slides, I often kind of remind you to use a standard library. This is one of these things that I'm not even going to bother doing it manually. I really, really want you to always use standard library for this. And the reason why is there's a few things. Number one, by using a standard library, it's more compatible, right? Other people use a standard library and you both have the same interface, same types, it all works together. Um, Additionally, since it's a library component, hopefully it's correct, and so less chance you get it wrong. It's also less to write, right? It's already there, you can just use it. And then finally, for other people looking at your code, they should hopefully be familiar with this, and so it makes it easier to read, right? Oh yeah, this is a standard chisel thing. I've seen this rather than doing this. There actually are a lot of subtle variations on things like ready valid for kind of doing this handshaking decoupling. Our own Professor Jose right now here actually has his own elastic, communication protocol signaling techniques he has for some of his other work in Pyro. So there are a lot of variants, but unless you know exactly why you want to use one of these other variants, use ready valid. And of course, we're using ready valid. Um, and so, yeah, so that's great. So how does it work? Well, you simply just take the thing you want to send and wrap it in either valid or decoupled. And now we know from what we learned last time that behind the scenes, it's really just an apply method inside the object that's actually doing that, right? And it's, returning a little bit of chisel. It's not even a module. It's just a little bit of chisel, right? We just learned about how doing chisel outside of modules last time. So for example, what we were just talking about, it's referred to as decoupled, right? So if I mark something as decoupled, it's going to automatically insert ready and valid ports into that thing I'm talking about. This allows it to do two-way communication. I'm sending, the receiver can do give back pressure. Interestingly, there's actually a simpler form we didn't talk about, which is just valid signaling, saying the producer marks the data sending as valid, meaning I'm sending something this cycle, or invalid, meaning I'm not sending anything this cycle. The consumer has no ability to say no. The consumer is always assumed to receive it if it's sent. And this is fine for many cases, right? And so the valid is kind of just, marking, hey, there's legitimate data being sent right now. So you can kind of think it's almost like the option type we learned about last time, right? It's almost like an option in a way where it's like, hey, is this thing empty or is it actually passing real data? One small thing about ready valid signaling, this is true in general, and this is no exception, is that when building a hardware design, we're going to try to avoid combinational loops. Sometimes, if you're not careful, people will say, "Oh, well, I only want to, be ready in this case if it's validated coming, or somebody use ready, or if it's so." What I'm trying to say is, if you use ready to compute valid or valid to compute ready, you could put yourself in the potential of having a combinational loop. This is one of the things that people at first say, "I'll never do that," and then one day you're doing something, and then you do it, and like, "Oh, I did it. I knew this was gonna happen." So yeah, so um, usually ready and valid should be derived independently. They shouldn't be dependent on each other. Because if they are dependent on each other, you run a chance of having a combinational loop. Okay, so let's go ahead and see this play out. Well, we might be saying, or what is a combinational loop? Well, so a combinational loop is a case in hardware design when you have uh, uncontrolled feedback. In other words, you have circuits flowing through and there's no state elements to hold things back. So, something like a register of memory, in addition to holding state, actually also provides synchronization, right? It says, hey, don't change so fast, only change on the clock boundary, whatever else you're doing, right? And so usually you use those for feedback. But if you don't have that, bad things can happen. So for example, here I have an adder, wire like an accumulator, but there's no actual state, right? It's just feeding the input right back in. So this is going to cause problems, right? So for example, if I try to run this, actually, fortunately, the chill tool is going to tell me I have a combination loop. They can detect combination loops in your design. So if I actually, instead of having, the output be dependent on itself, right? There's no end to this, right? Count depends on count plus one, right? So like, how does this all fit together? Of course, if I put a register in there, it's just fine, right? So we do want to avoid combinational loops. This kind of small size kind of reminding us of that. Just gonna yell at us, yikes. Yes. It's not quite deadlock. So combination loop is not quite deadlock. It's more uncontrolled feedback, right? Where it's kind of like, what's the right value? Um, the deadlock is, both sides can't move forward because, they're dependent. One side is dependent on something the other side has, and vice versa. With combinational loops, how it behaves actually varies on the combinational loop. And so that's why the tools usually don't want you making these. So some combinational loops will oscillate, where you'll get like one value and that value will cause another value. So like it oscillates really fast between two values. If you heard something, So you can sometimes for people to test out circuits, there'll be something called a ring oscillator, which is a combination loop that's built intentionally. It's actually just many inverters in a loop, and so it keeps inverting the same cycle back and forth. And so yeah, it'll keep changing. So one behavior of a combination loop is oscillation, or just constantly changing. Um, Another behavior is it becomes metastable. It reaches some in between values. So it's not 0 or 1. Like it's locked halfway between voltage wise, and the circuits kind of like latch up and it can't change. That's bad. Uh, Interestingly, there are cases you can have a combinational loop, but based on the nature of the logic functions, it converges and it stays there. Um, and so there actually are a handful of cases people do intentionally build combinational loops and they trust it's going to converge and they know it's going to converge and even prove it's going to converge. If you're doing that kind of stuff, maybe Chisel's not for you, but there are people who do that. There are people who do stuff, for example, as asynchronous computing, where they build large systems without clocks. They have a hard time when they use conventional tools because they usually have lots of combination loops, for example. Um, but other than that, you usually want to avoid it. Yes, go ahead. No, you cannot make a ring oscillator in Chisel. Yeah, it's going to yell at you. So how would I make a ring oscillator in Chisel? I would probably sheet and use a Verilog black box. But in vanilla Chisel, it's going to flag you for a combinational loop. Okay, so let's see some examples of this in code. So if we tried to just use valid, so notice here we have, some simple module that, has some input is taking of some number of bits, and then some output, and then we can put an enable signal on it. In other words, this is really just kind of doing a pass through and just kind of showing this valid construct that works. So notice how valid just wraps it like this. By default, valid's in the out direction. So yeah, so we go ahead and write this up, nothing too crazy, right? Basically, if this is valid, is dependent on we're connecting to it. So notice how we declared out just as out. Valid is going to return a bundle, right? And that bundle is going to have two fields, right? It's going to have dot valid and dot bits, right? So dot valid we need to connect, and dot bits we set to the end. So for example, let's say I forgot to connect dot valid. It's going to yell at me because hey, I have an I/O that's not being driven, right? I have an output here that nobody's setting a value to. And I'm curious if I do this, we will find out what happens. There should be a type mismatch. Let's see. It's hanging. So remember when it hangs in Jupyter, sometimes that means there's an exception being triggered, but the way the error handling is we can't see what's happening. But yeah, it's not good. Okay, so yeah, why the type mismatch? Because out isn't a single uint anymore. It's now a bundle which has a bool for valid and a uint for bits. Or actually not, it's a uint, whatever was passed to it. In this case, it was a uint. Cool. Yeah, so this is just using valid. Um, Now we can do a little bit more. So okay, in this case, we can do receiver, right? So okay, so let's say someone is now receiving a valid thing. So remember, by default, valid's in the output direction. So we want to make it an input. We're going to say it's flipped to reverse the direction. And basically, just we're going to look at that field. So whenever there's a one on the valid marking the data, because there's simulation, not real hardware, we can go ahead and print out the data that was sent. Meanwhile, in our test bench, actually, fine, we can go print this out first. Let's go print it. Sure. Okay. You can see because this is simulation. The prints, you can't put those in hardware, but you put those in simulation. That's what's going on. But okay, ignoring that detail, let's go ahead and look at our test bench for a second. So our test bench, we're gonna run for 8 cycles. We're always gonna poke the cycle number in for the data. Why not? To make matters interesting, we're only gonna be valid on even cycles because why not? So we're gonna say, hey, on even cycles we're valid. On odd cycles, it's gonna be not valid. So we're going to see what happens when we only send valid some of the time. We can see what happens, right? Okay, cycle 0, the receiver says, yeah, hey, I received 0, because valid was true, right? Cycle 1 means we're poking, a zero into the valid because one's not congruent to two, right? And so you see, okay, so we're receiving even numbers, right? So if I want to change this to send on odd cycles, fine. Now we see it gets the odd ones. But this is just showing that this is kind of nice, right? All I have to do is kind of set valid when I want to, and then on the receiver I can just do a when statement and kind of act on it accordingly. So this is one of those cases where you could do this with a mux or something, right? But with the when, it's a little bit kind of more graceful to kind of capture, here's a condition that's happening, and then I want to make certain connections based on that. Cool. Okay. So that was valid, which remember only adds in the valid signal. If you want both the valid in one direction and the ready in the other signal direction, we need to use decoupled, right? So, okay, so for decoupled, it's similar. We go ahead and wrap up the thing we're doing in this case. In this case, it's an anonymous uint. So now remember we have on the output side, we need to connect up valid like before and bits. There's now going to be an input coming into our module for the ready, right? So notice how we have ready on the right side of a connect statement because we're actually using that as an input to us. That's coming from the receiver, right? So in this case, what we're going to do is we're going to count when they're ready, right? So this model takes an enable signal. So someone's going to tell us, hey, when that's one, you're valid, you're trying to count. We're actually only going to actually count when we're told to count and the other end is ready. And if that's the case, we're going to go ahead and advance the counter. So here I'm using the chisel counter, that's the standard library counter. So the first argument is the enable, when should it count? Second argument is the maximum value. And so yeah, and then of course, we get two things back and we're going to use the count as our output. So after all that, what happens? Well, you kind of see the key points, right? Okay, so no resets to zero. Otherwise, we advance and there's a wrap value. What is wrap value? Well, it's the count plus one, right? Okay. And if I make this some different number, you're going to see you have to get more clever about having to wrap, right? But because we're using the standard counter, it's smart and recognizes a weight, it's going to naturally wrap around on its own. Yes, go ahead. In this case, I don't think so because we don't know the nature of how ready and valid are used on the other end, right? So we are binding them together in this case, but this isn't a combination loop until the module on the other end does this, right? So in this case, we've connected these two things together, right? So if you imagine drawing as a box, right, you'd have, here's a box, here's ready coming in, is connected to valid going out, right? So I've made a connection between those two things. That's like half the loop, right? So we need somehow to connect our valid to the ready and the other end to get the full loop. And so as a design principle, technically, you can connect ready and valid on one side. You just can't do it on both sides. But from prior experience of avoiding combination loops and doing larger hardware projects, my advice is to never do it, and then you're okay. Because if you only do it on some of the times, then you're fine most of the time, and all of a sudden one day you connect something, and all of a sudden it blows up in your face. And the reason why was, you had another one you didn't think about, right? So if you never have loops on either side, you never need to worry about this. But you're right, technically, it would only need to be on one side. If it's only on one side, you're still okay. Yes, yeah, we reached out of a recording. The sentiment expressed was, um, you know, this perhaps is a more representative way to represent the valid signal because, the counter does not advance unless ready's telling it to advance. And so this is one of these things where I think there's a lot of times where, we know that the transaction occurs and ready and valid are both true, and our willingness to do something is kind of dependent on the other side. The way I've made pieces myself over the years is I think of it as what are you able to do, right? And so, yeah, the truth is the counter is ready to count. Doesn't mean it's actually counting. It's able to count. And in fact, it's actually not counting as cog data side. So yeah, it's one of these things where you got to be really careful when you define your semantics for your modules, what you mean when certain things happen. When it comes to ready valid signaling, my mentality is, both sides should independently indicate their status, hopefully without using the other side, and then, the transaction occurs when they're both true. So just because, valid is true in this case, depending how you specify your documentation, that either may or may not mean it's actually advancing the counter, right? In this case, it says count when ready, right? So we're only going to count when they're ready. Just because I'm valid is, reflecting the fact that someone told me I'm enabled, right? But this is one of these things where, be careful naming, be careful documentation. Yeah, cool. Okay, so here we did it one way. In a second, we're going to use a convenience function. So, one of the things about having Chisel and Scala is we can kind of keep building stuff up, making your life a little easier. So this is a common pattern, right? This notion of having, setting ready and valid in a certain way, maybe doing like a when on something. And so why not write some Scala to make that easier? And so, for example, fire is looks like a method, but it's actually like a bool that's true if and only if we're ready and valid, right? In other words, is there actually data being transferred? Um, Likewise, let's say I want to send something. So in some ways, it looks kind of simpler for me to say, hey, enqueue this data. This is automatically internally going to go set the bits and set valid to true. I don't need to do all that manually. Um, or maybe I want to be clear that I'm not sending anything. Or on the other receiving end, you can, DQ or no DQ. So let's see an example, right? So for count when ready, in the first example, we set these things manually. Here's kind of a scenario, right? So let's say the IO enable is true. So if I, say, hey, in that case, enqueue the count, I am requesting to send that data, right? There's no guarantee the transaction occurs at this point, right? Because here I comment out what it's doing effectively, right? So we're setting not only the bits to count, we're setting valid to true is what this is doing. It's doing both of those things for us. But perhaps this is easier syntax in these two lines. Perhaps, right? Alternatively, if you're not sending data, normally it's sufficient to just say, hey, valid is false, and you don't really care about bits. Bits should be a don't care. If you want to be explicit about bits being a don't care, there actually is a don't care in Chisel for that kind of situation. And if you use the .no in queue, it's going to go ahead and actually attach don't care for you, so that we can convey that. So let's go ahead and see how this looks in Verilog. And I think it's easier to make it smaller sometimes. Okay, so yeah, you can see the outputs are count. And like, wait a second, is count not X? Yes. Don't care means the tools can actually just make the connection rather than making its life hard on itself. But if we were to go ahead and run the test bench, this is like from before, we're going to count under certain circumstances, right? So in this case, we're counting on odd numbers. We could count on even numbers. And you can see it kind of keeping it similar for 2 cycles is waiting for the next time to count. Cool. Questions? This is just the producer. This is just the producer. The count when ready is just the producer. So the couple is in the output direction. That's all it is. And then in our test bench, the test bench is acting as the consumer, but it's kind of not a real module. It's kind of like a test bench with faking things. And so, yeah, as the consumer, the test bench is saying ready is true every other cycle. Cool. Okay, so now that we have these constructs for ready and valid, uh, what if we want to start using them? So the reason why we did this is that actually a really handy thing in the Chisel standard library is a queue. So you can imagine ready and valid are great for if you, add decouple, if you have like a single data element. But actually sometimes you have bigger components, and you want to have queues between them, right? So queue can have multiple elements inside there, and it's a great way to kind of have a more robust system, right? Where you can imagine um, if the producer produces a lot of data and it takes the consumer time to process it, you can put things into a queue for it, and then the producer can go off and do something else, and the consumer can kind of keep draining things off the queue, right? So, this is queuing theory or computer architecture. Basically, a queue can help spread out burstiness, right? So I have a lot of production or a lot of consumption. The queue can help for that. The thing that queue can't do, it can't change a fundamental throughput mismatch, right? If producer is always producing data twice as fast as the consumer, your queue is going to fill up, right? And that's not going to change, right? So if you have a fundamental throughput mismatch, the queue is not for that. If anything, it's actually better to have a smaller queue because otherwise you're just waiting and burning harder for no benefit, right? And so actually there's a interesting research, which you're all probably too young to be aware of, 15, 20 years ago when Wi-Fi was first coming out, where they were trying to make Wi-Fi work well, and people were adjusting their TCP parameters and trying to make their network just right. And I wish I remember the name of this problem, but basically the issue was that using conventional network techniques, you would make your TCP buffer size bigger and bigger and bigger and bigger and bigger and bigger and bigger. And it's actually making really bad outcomes because you actually have like long latencies and long delays, lots of memory. In terms of actually making your TCP buffer smaller, actually way better performance, right? So sometimes, you can definitely have unnecessary queues, but there are times they do want queues. And the whole point of queues are for handling burstiness, right? Variation in production and consumption. That's what they're for. And what's nice is in Chisel, the standard library provides a queue, and both sides are decoupled. So you can imagine that, hey, under the producer, I can enqueue things. So the reason why I labeled it enqueue here, this is the name of the port on the queue. So the enqueue is this side, that's the dequeue side of the port of the queue. So I can, keep putting things in the queue as long as there's room in the queue. The queue is going to keep telling the producer it's ready, right? And whenever, it's ready here and valid there, we're going to do a fire and send something, it gets put inside the queue. Likewise, on the dequeue side, right? If the queue is not empty, it's going to tell me it's got valid data, right? And then if this side is ready, it will, when both are true on the clock edge, it's going to remove the element from the queue and the queue is in advance. And eventually, if the queue becomes empty, it's going to stop telling the consumer it has valid data. Okay, so yeah, like I said, queue is part of standard library. Here is nice to just draw it as, the enqueue port, the dequeue port, and saying they're decoupled. We know that a decoupled internally has ready, valid, and bits. So actually, if I was to draw that same diagram from before, this is more accurate, right? There's the data payload flowing into the queue and then onto the next thing. And they both have ready and valid. So you can see this queue already has 6 freaking ports, right? It was just 2 decoupled ports, but very quickly kind of blows up in his face, right? Cool. Questions so far? Yes. I think I have an example of that next slide. So fire just a convenience for when it's ready and valid at the same time. I don't have it here, but if you find yourself writing when ready and valid, you can just say when fire. This is one that helps. Oh, yeah, it is. In this case, yeah. So in this case, we are counting into the queue. So when the queue has room and we're able to do a transaction, we're going to advance the counter. So I do have one. Okay, good. I do have a do without fire example. Good question. Correct. Yeah. So to respond to the question is a queue sets its ready signal based on it having space. The reason why it's not 100% true all the time is these next few lines. So going in more detail with the chisel STL, standard queue provides. You give it a type. Type has to have a size usually. Number of elements, sure. There's actually 2 additional arguments that you can specify or you can leave the default values for. So one is this issue of when is it full? So some might say, okay, if every slot in this queue has data in it, that's a full queue. What are we talking about? Well, if I know for a fact that someone's dequeuing this cycle, there's going to be a spot opening up. So you can imagine that, if you're really clever at optimizing your queue, you could have a full queue. You can simultaneously enqueue to dequeue at the same time, right? It's a net zero change in occupancy. If you don't have the capability to do this, you would need to have a full queue, recognize you're full, drain one element, and then insert the next cycle. So basically, this optimization allows you to, with a full queue, continuously enqueue and dequeue at the same time. Without this optimization, you kind of are forced to NQ every other cycle and DQ every other cycle. You kind of keep going full, not quite full, not quite full. And so this capability is called pipe, is the name of the argument for the queue that does this. Um, it's just kind of a small deal. So basically, if you're full, you're allowed to still NQ if you're DQing at the same time. So in other words, what does that mean? That means that if this pipe parameter is true, this ready signal coming out of the queue depends on the ready signal here. So the reason why this is a optional parameter, because it seems like a good feature, is because, hey, there's a connection here. So depending on how you use ready and valid elsewhere, this could cause a combinational loop. So thus, they give designers the choice to turn this on or off, because sometimes you don't want this, because you don't want a combinational loop. As another similar connection or functionality is this flow parameter. So in other words, if the queue is empty, why delay things, right? Why not just have a combinational fast path that goes by all the memory elements inside the queue and just goes straight from here to here, right? If this is empty and this person's ready, let's just send it straight through. That's the flow parameter, right? And so that's really cool. But you also can imagine, wait, flow in that case is going to look at the queue size and ready, and then pass this straight through. So once again, making connections between the ports on the queue, and depending on how your queue fits into your global design, and maybe it does or does not cause combination loops, so maybe you want to disable this feature. That's why these are options, right? They aren't always set one way. Okay, let's go ahead and do a quick demo. So sometimes it's hard to kind of take these components and squeeze them into one slide, but this is my best attempt at it. So, here we have this hypothetical module. We're going to instantiate the STL queue. And what are we going to do? Well, we have a counter, and we're going to count numbers and put those numbers as we count them into the queue. So this kind of, okay, so the counter going into a queue is what the topology we're building is. So we kind of see how it fits together, right? So for example, so the bits going into the NQ port of the queue are the counts. And, when is it valid? When are we actually putting into the queue? When the IO is enabled, right? So we have some sort of external enable for our module. When that's true, we are going to try to put things into the queue. Now, is the counter going to advance? No, the counter is only going to advance when it successfully puts things into the queue, right? We don't want the counter to advance if the queue is full and it's dropping what we're doing, right? So this is the same as, NQ.ready and NQ.valid being true, but it's easier to write .fire, when they're both true. Cool. Now, what about the other end? The other end's actually easy. We just say our output's decoupled, and then we just bulk connected it. Okay, that was cool. We're done. That's not three. That's not three connections. Okay, simple. And then for visibility into doing debugging in the test bench, I pulled out count as an IO just so you can see what's going on. But remember, at the end of the day, we're actually counting into the queue, and then the queue's output's attached to the output of the module normally. So normally, if you count, it might take some number of cycles to go through the queue before it gets to the output. This count port is kind of like a way for us to peek and see what the current counter value is for our stuff, right? Cool. Num entries, yeah. Yeah, so here, for this example, I'm taking parameters as this generator, right? So I can set the number of entries. I can also actually set these pipe and flow parameters and then passing them into this queue. So it's a kind of a lot of code I've written around, I'll make sure we don't go past time, a lot of code I've written around the queue module, make sure it kind of does what we want. Okay, so we just talked a second ago about these various queue behaviors. Through the test bench I wrote, that kind of does three different phases. I'm going to kind of play with this, right? So the first phase, we're going to try to fill up the queue. So how do we do that? Well, we're going to try to enable the front end, right? We're going to say, hey, go ahead and count. We're also going to tell the output side of the queue we're not ready, meaning the queue is going to take values in but not eject them. Okay, so maybe if I go ahead and even comment these out and maybe make this a little bit smaller so you can see what's happening and run this, and we get an error because I didn't run the pass cell. Okay, so if I go ahead and run this cell, we see what happens, right? So we see, and we're kind of reminding ourselves what's happening, the counter is counting up, right? So yeah, there's still room in the queue, we're counting into it. However, the output's still zero, right? Why is the output zero? Well, initially, there's nothing in the queue. Now there is something in the queue, so the output of the queue is valid, but because we're not actually taking it off, we're filling the queue, it's still zero. It's still that value. And I can change some of these numbers to kind of see the behaviors, right? For example, let's say I make the queue a little smaller. We're going to see the counter stops counting because it gets to value 2 and it can't get beyond 2 because the 2 hasn't gone into the queue yet, for example. So in this case, we have a 2-entry queue, and it's still there, and so that's why it's still going on. Um, okay, cool. Anyways, so that's us filling the queue. Cool. Now we're going to drain the queue. So how do we drain the queue? We're going to stop counting, and we're going to turn on the output, right? So now we're going to say the output's ready, so we can start letting things come out the other end of the queue. So we're going to fill the queue up, stop, and then start draining. Okay, let's see how that behavior goes. Okay, so we see, for example, it counts up, the output stays the same. Now the output advances because we're draining the queue, and the counter is no longer advancing because we turn off the front end. Cool. Okay, now for the third case, let's NQ and DQ at the same time. So remember, after this middle phase, we've now drained the queue. It's empty, right? It was able to DQ things. True, 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 true. It's valid. It's a 3-entry queue. We took all 3 elements out, and the 4th cycle, right? There's nothing there left. That's why it's not valid anymore. Now, if I do simultaneous NQ and DQ and you make this a little bit smaller, it's going through, right? So remember, we drained it all the way. And then, okay, yeah, then we get the 3 in there and out of there, and then the 1, 0, and the 1. So it's kind of going in. Because it's empty, and then we put one element in, and then we drain that one element, it's a 3-element queue. And so the producer side is being told, hey, you have room. So it keeps putting in, the consumer side keeps draining. And so here it keeps having size, capacity of 1, right? Sorry, occupancy of 1. Okay, instead of draining it, what if we fill it up and then go straight through, right? So if we fill it up and go straight through, what happens? Well, in this case, why is the counter not advancing? Oops. I need to also comment out this line. The output's ready to receive. Okay, so the output's ready to receive. So see, initially when the queue is blocked at the other end, we fill it up. And now we are, NQing and receiving at the same time. But this has the pipe parameter set to false. So you can see what happens is that, at this point it's full. And we actually spend 2 cycles at 3 here. Actually, technically 3 going back here because the queue is still full. We actually need to wait for the 0 to come off before there's room for it to come on. If we set this to true, it's able to put NQ 1 cycle earlier, right? It's able to now NQ when the queue is full because it knows it's going to DQ. That's that pipe parameter in action. Now, likewise, for this flow parameter, we're going to need to drain the queue, and then it's going to go straight through. Oops. Do I need to adjust the sizing? Because right now there's one element in there I'm trying to figure out. Oh, sorry, I didn't change flow. That's why I didn't change. Yeah, so now they changed flow. So the queue is full at this point, became empty, and now I'm able to just pass things straight through because it's an empty queue, but the other side is ready, so it's going straight by. This is an example of that flow parameter. Cool. So yeah, this is the queue. That's a really helpful module for us to use. These subtle details of pipe and flow, the subtle details, these are kind of how it behaves under certain corner cases, and depending on your design scenario, that's the useful to you. The bigger picture here is to be familiar with the notion of, hey, the queue has an NQ and DQ side, and I can use ready and valid with the couple to kind of signal that. This is an example of in Chisel where, we are very quickly kind of building up abstractions and using them, right? We had this decoupled abstraction, and putting a couple ports, all of a sudden we have a lot of ports in hardware, right? If I look at the Verilog for this, we're going to see a lot of stuff, right? Uh, so I won't explain what's going on in the Verilog, but I will say that in a future lecture, we actually use an Agile approach to build up a queue. And what we're going to do with that is we're going to start with a single register and multiple registers and eventually show different ways to build it internally. And by the end of that lecture, we're going to have something similar to what's in the standard library. And as an interesting note, I had that lecture, I wrote that, I guess, 2 years ago, and it was mostly correct. And then last year, I had a special guest speaker who does formal verification with Chisel, and he used that lecture and he found some subtle bugs in my intermediate queue designs. And so that was kind of cool. And so now that lecture should be fixed thanks to his contributions. Thank you, Kevin Loeffner. But that's an example of that. So it's kind of showing these things fitting together, and you can kind of build abstractions and go from there. Cool. The number in parentheses is the value on the bits portion of the bus. And it's not the occupancy. There's not an easy way from the outside to know the current utilization of a queue. You just know if there's something, you just know if it has data or does not have data. That's all you know. Um, so in this case, the way I set it up is I have a counter counting into a queue. And so based on the number coming out of the queue, you know when it was queued. And I deliberately have the counter count one more than there's spots in the queue. So that way you can kind of see the behavior when it fills up and how that handles it. Good questions. Okay. Well, cool. I think that's it. I just want to remind folks about the assignments coming up. So homework 2 is posted due to Sunday. Lab 2 is due on Thursday leading up to it. Um, and I'm going to reconsider the weekly due dates to make sure they line up better with my office hours. My office hours right now on Mondays, so it seems like not a very useful day. So I might move my office hours, move the assignment deadlines or something. So this week deadlines are set. The homework, yeah. I mean, so we have this conversation as an instructor. It's one of these things where you want to be helpful in office hours. You always are a little nervous having office hours on the last day because you don't want somebody to put off working on it until they talk to you. And it's like that's why sometimes you want to have your office hours like 2 days before a deadline or a day before a deadline rather than the last day. So that's why I need to look at my schedule and see if we have room for me to push back the homework deadline, or I might just change my office hours to Friday or something. I don't know. We can see what makes sense. But yeah, I think the current schedule is not quite optimal, so I'm trying to adjust it. But the deadlines for this week are set. I'm not going to move those on you. Cool. All right. Well, have a good day.